What is happening, my calculus brothers and sisters? Mr. Record here from Avon High School. We are going to take a look now at topics 8.7 and 8.8. Now, the purpose of this video is only going to be on the first of those topics. We are now going to go crazy 3D, and we're going to start talking about volumes. So let's get right to it. So what we're going to see here in our first topic is volumes with cross sections using squares and rectangles. And basically, as the words say, we're focusing now on 3 dimensions instead of just 2 dimensions. Makes a big difference, and it really lends itself very well to a lot of manufacturing type of scenarios and things of that nature. So how do we do this cross section? First of all, well, what is a cross section? Well, let's help out with that. You take a ball, and if I were to cut this ball right down the vertical plane, and if I were to open this ball up, hopefully you would all see a circle. That's what we mean by a cross section. And I could do the same thing with other shapes like this bottle, a cross section opened up, another circle. Now I could try to get cute and do it with, say, a mouse, but then things get a little bit different because we don't really have a nice geometric shape that we could call the cross section of a mouse. So we're going to stick with some very familiar cross sections. And those are going to typically be the square, the rectangle, the semicircle. Oh, and the triangle, almost forgot. So you can see here in the blue, I've got basically your general formula for the volumes of solids with known cross sections. And it probably makes sense that if you take something like area and just kind of contemplate this, if A of X is the area, right? And we're taking cross sections perpendicular to the x-axis, we'll focus on that here in a bit. Area is always measured in square units, right? We know that. Volume, we always know, is measured in cubic units. Well, I don't know about you, but boy, it makes a lot of sense when you integrate squares, you get something that's cubed. And so it really comes together nicely when you think about this particular relationship. My picture there is a picture of the Kauffman Center for the Performing Arts in Kansas City. Kind of looks like a little uh, structure that's built upon cross sections. But the ironic thing is that particular calculus looking building is right across the street from the Kansas City Convention Center, which in most years, normal years, is where the AP Calculus exam free response questions are graded. So in order to make this work, we have to know information about 4 basic shapes, and we have to know the area of those 4 basic shapes. So what are these pieces of info? If you're talking about a square, you need one thing and one thing only, and that's the side. And we can call that S. All right, knowing that, then the formula for the area is just simply side squared. Pretty easy. Move on to the rectangle. There are 2 pieces of information that we need to know. We need to know a length, which we're going to call L, and we need to know a height, which I'm just going to go ahead and call H. Once you know those 2 things, the area formula falls into place very nicely, L times W. Now, the same thing is going to be true about our other shapes, the semicircle and the triangle, but I'm going to hold off on sharing those with you until we get to the next video, because we're going to talk basically only about topic 7, which is squares and rectangles, and then we'll move into the semicircles and triangles when we get to topic 8.8. But the great news is that they both utilize the same formula. You're integrating area. Let's take a look at our first example. We have a volume of a solid in which the base is the region bounded by the graphs f of x equal 1 minus x over 2, g of x is -1 plus x over 2, and then we've got this stray x equals 0. So I'm going to, in typical fashion, sketch each of these using different colors. The f of x will be in blue. Don't fret if this bothers you for a little bit. Think about it a little bit closer, and you will come to the realization that this is just a line. We're just trying to mess with you, folks. This is a line that has a y-intercept of 1 and a slope of -0.5. It's just reordered to be a little bit more confusing, but that's all that we've got. Slope of -0.5 would look like that with a y-intercept of +1. And then, let me scoot out of the way here. Let me see if I can get a good angle on this, and we'll connect these dots. And lo and behold, when those points points are connected. There we have a line. Of course, we don't have an enclosed region, so we move on to the next, g of x. If we sketch him, y-intercept is -1, slope is up 1 over 2, up 1 over 2. We can cheat. It's the only time you're allowed to cheat. Go down 1 and over 2, and we connect those. Oftentimes, I use the analogy, you're a cattle rancher in Montana, beautiful country, Montana, and you want to corral your cattle so they don't roam places. Well, if these are the fences that you used, you're not going to make a lot of money as a cattle rancher because your cattle are either going to go to Canada, Mexico, the Pacific coast, or the Atlantic coast, right? We don't have an enclosed region. But that's why we have another graph, x equals 0, because that is just a fancy schmancy way of saying the y-axis. And so if we sketch him, we now have an enclosed region. Our cattle will not roam free. So there we go. Now, where else do we go with this? Well, from here, we are going to think about placing a representative length. Now, I might call this a rectangle, but really what it is just some type of length of really irrelevant thickness. I just wanted to draw it thick enough so that you could see it. And then we basically have a square that's coming out at your face, just like that, just like that, just like that. Now, if I were a better artist, man, I could just nail this, right? I could do this, but I don't know if that necessarily does the job, right? That's a little tricky. I mean, if I try to draw more and more of these, are you really seeing what's happening? Well, maybe you are, maybe you're not. That's okay. I've got other manipulatives that I can use, like right, like right here. Right, I have my wonderful little foam squares that I've made, and you could think of that particular shape as looking something like this, right? Well, see, the back is all nice and flat and flush right here with my hand, but then I have this kind of pyramidical shape of squares all stacked together. Well, maybe that helps, but you really don't have to see it to find it. That's what's great sometimes about calculus. So what we can do here is we can rely on the information that we talked about on the previous slide. What are the most important things in part A? Cross sections perpendicular to the x-axis, which are squares. Well, for a square, we need to know what the side is. The side is always defined to be the top curve minus the bottom curve. That will never change. So if we take the top curve, 1 minus x over 2, and if we subtract the bottom curve, -1 plus x over 2, we have got a very reliable expression for the side. And we actually can simplify this expression, and we end up with 2 minus x. You can double check and make sure that that's true. And just so that you know, and a lot of students don't quite get why does top minus bottom work, and I want to show one quick example why it works. I can put this square about anywhere. Maybe I decide to put it there. I know it's a little longer than it should be, but I could always adjust it if I wanted to, et cetera, et cetera, et cetera, if my computer will let me. Sometimes my computer won't let me, but you get the idea. So I can adjust it a little bit, maybe look all crazy like that. But anyway, let's put that square right here at 1. In fact, what I think I'm going to do is just draw another square or another rectangle. So what if I have this rectangle that I'm putting right here at x equal 1? Well, by golly, if you plug 1 in for the x, 2 minus 1 is 1, I would certainly agree that the length of that is 1. It's like a half up here, it's a half down there. And I could put this anywhere I want, and I could choose any x, and this is going to spit out the exact length. And so that's why top minus bottom is always going to be your friend. All right, so next up, you're going to be thinking about area formula. What is the area of a square? Well, that's easy, side times side. Okay, what does that mean in the context of our problem? 2 minus x quantity squared. And now all the hard part's done, because to find your volume, all that you need to do is integrate that area formula with respect to x and do so between the boundaries 0 and 2, because that's where we start at 0 and that's where we end at 2. In fact, every one of the problems in this example are going to be set up with those same limits of integration. Now, as far as integrating this, you can FOIL it out, expand it out. You could use U substitution. They both work about the same amount of effort. So I'm going to go with the expanding out. So that would give us 4 minus 4x plus x squared, I believe. And then when we integrate that term by term, we get 4x minus 4x squared over 2, which of course is 2x squared, plus x cubed over 3. Evaluate from 2 to 0. And then when we replace all of these x's with 2's, we get 8 minus 8 plus 8/3. And then, of course, subtracting 0 is just going to give us 8/3 as an answer. So there you go. Next up, we're going to take a look at part C. Cross sections perpendicular to the x-axis are now rectangles, heights of 3. You're going to find out that rectangles might even be easier. And here's why. You've already done the dirty work. You've already found that the length is just the top minus bottom, which is 2 minus x, because we're not going to recreate that. We know the answer. And we're told that the height is 3. And hopefully we realize that the area of any rectangle is the product of those two. You can even distribute the 3. I wouldn't. And now we just go into our volume formula and we integrate 3 quantity 2 minus x with respect to x. And once again, our boundaries are 0 to 2. And when we finish this up, 3 can come out in front, integrate 2 to get 2x, integrate x to get x squared over 2, and we're well on our way to finding yet another area. And we got to use our best friend 0. I don't know about you, 0 is my best friend. He is my buddy. So 2 times 2 is 4. 2 squared is 4 over 2 is 2. And then when my buddy gets used, everything becomes 0. So 3 times 2 is 6. And boom, you have your next area. Now you want to stay tuned for a video coming up later on in the series where we're going to tackle part B using semicircles and part D using equilateral triangles. But what I am going to do, even though it's a bit unusual, we're going to move on to example 2 now, and we're going to tackle just part A, because in part A, the cross sections perpendicular to the x-axis are squares, which is one of our 2 shapes that we're studying in 8-7. But notice how we have a bit of a issue up here. Find the volume of the solid in which the base is a circle of radius 3 units whose cross sections are described. Well, there's one thing I want to do here. I'm just feeling a little bit gamey here. I want to change this problem. I want to change, if you all don't mind, I want to change this to 2 units. Now, if you're wondering why, I have a skill builder activity for my students where I use 3 units, and I don't want to do the same problem. And besides, 2 units actually works out a little bit rougher. There's some fractions, and I thought you guys were definitely up for that challenge. So let's go ahead and use 2 units here. Now, the issue here, there's a big issue because you were not given equations. And that might bother some students, especially if you don't have a really good background on what the equation is of a circle. That's not something to worry about, because if you're a calculus student, you can probably figure out circles equations in a 5-minute, 10-minute study on your own. But to expedite that process, the equation for a circle, if we center it at 0, 0 with a radius of 2, would look like that. Now, do we have to center it at 0, 0? It didn't say so. Absolutely not. But you're going to find out if you sketch this circle centered at 0, 0 with the radius of 2, it is going to be a little bit easier to work with. But the bottom line is no matter where this circle's located, it makes no difference where you put this guy. The volume that's produced, no matter where it is, using those various squares, is always going to produce the same volume. Okay? Now, let's reap the benefits of using the origin at the center? Well, first thing that we start thinking about doing is finding the length of this representative slice here, right? This representative very thin rectangle that's going to come out at your face, right? At my face too, and look something like that. And then I'm going to stack a whole bunch of those in here. All right. Well, let's take top minus bottom. Circle minus circle. Well, that's not good, right? Might think that that's 0, but it's not 0. The reason it's not 0 is because this is a calculus class. We have to work with functions. It's just the way it is. So we have to go back up here and we have to solve this equation for y. We got to make it look very function-ish, right? And it's going to, what's that? Oh, you want me to move? Okay, I'll move. It's all right. It's all right. There's that better? All right. So then we can get y is equal to plus or minus the square root of 4 minus x squared. Good job. That was worth moving. All right, so we have this all set to go. We have to think of the positive version of this square root as being right there. And we have to think of the negative version of this square root as being down there. Right. So now you can do top minus bottom, and you're going to find out that S, the length of the side, is nothing more than the square root of 4 minus x squared minus the negative square root of 4 minus x squared. And of course, that's going to be 2 square root of 4 minus x squared. We just doubled it up. And of course, you all know that the area is side squared. I'm not even going to ask. And in this case, that's 2 square root of 4 minus x squared, quantity squared. If you simplify the 2 squares, and later on here, you notice that the square root and the square cancel each other out, and you don't have to deal with that square root anymore. All that's left to do is write your volume formula. What's integration of 4 times 4 minus x squared dx. And your lower boundary, that would be the starting interval, -2, ending interval of 2. And hopefully that setup makes sense. And if it doesn't, if I've gone a little too fast, you're welcome to scrub back, rewind, and take a look at some of the explanations. We're going to move on to finding out this answer, but I'm a little saddened. I miss my best friend. 0 is my best friend, and 0 did not make an appearance here. But we can make that happen. And I would strongly suggest at least thinking about this. If you were to integrate starting at 0 and going up to 2, so you're using this as your shaded region, and stacking those rectangles there, or I'm sorry, those squares in that space, isn't that going to just give you half of the volume that you want? So in that case, you could multiply your answer by 2 if you just started integrating at 0. It's not something that you have to do, but it is something that you might enjoy because working with 0 is very easy as a boundary. You're less likely to make an arithmetic mistake. And besides, he is my best friend. So 8 comes out in front. We integrate 4 minus x squared. We have 4x minus x cubed over 3. And life is easy now because of our 0 boundary. 8 multiplies by 4 times 2, which is 8, minus 2 cubed over 3 is 8 cubed, 8 thirds, sorry. And then we subtract, and then, yep, by the time we plug 0 in, everything here in the parentheses is going bye-bye. And the final answer is 8 times, this is a little tricky, 24 thirds minus 8 thirds, I want to say is 16 thirds. If you want to do some more simplifying, I think 16 times 8 is 128, and that would be the most simplified answer. But, you know, just between you and I, most every teacher, and I'm probably likely that your teacher is one of them, the AP exam will certainly accept that particular answer, not simplified. and there's your square. Notice the other parts of this were semicircles, equilateral triangles, and more right triangles. And so we're going to put those together with the remaining parts of example 1 in our next video. Hope this helps. If you like what you're seeing, make sure you hit the subscribe button. Always study your calculus, and we'll see you next time.